the expensive one.
So let me start talking about okay. Probably this part will be very basic. So sorry for whoever have a bit of it, but Q will be a finite Quiver for me. The zero are the vertices, one out. Then, in order to define the representation, we have to fix. We can take the dimension of the representation, which is an element, and zero, which is Q of dimension B, which is defined like for any arrow ij into 1, I take homomorphism. I take a linear map from for each arrow that goes from bi to bk, the arrow goes from the vertex I to the vertex j. Now, on this space, we have a natural action of a group, which depends on the Quiver, of course, but on the dimensional vector also. This is the gauge group for our theory, also. And it acts naturally. Okay, so this one is defined like the product over the vertices of general linear group of the vector space placed on the vertex, and it acts by changing the basis of our vector spaces. Okay, now in order to suppose you want to study moduli space of this space here by this action, we can take some deformation of the Quiver in order to have deformation of our quotients. These deformations are, it's called the framing of Q, and it corresponds to take another Quiver called the framing, which is given by adding to, for each vertex of our previous Quiver, we add a copy of it, and we add a map going from up to below. Technically, this is not important to construct a continuous square varieties a priori, but in giving an orientation, it's a symplectic structure. We have a magic way. So we can consider the representation of this new space, of this new Quiver, sorry. Of course, we have to fix a frame dimension vector, so dimension vector for the new vertices, W1, W2, W2, sorry, 0 and 1. We have this space here, and we again have the action of G over this space because we are just changing the basis of the vector space placed on the original vector, right? Okay. At this point, we can modify again this space, and we consider it is cotangent space. But now, cotangent space is the direct sum of cotangent space of homomorphism between two vector spaces. Now, the cotangent space of vector space is just B times its dual, and the dual of such a space corresponds to homomorphism from Vj to Vi. So basically, we are considering T star of ref Q VW is nothing that the representation of, let me call the framing QF, the double of the framing VW, where the double is obtained by inverting every arrow in our construction. Now, since this action, GB act over rep QF VW, we can take the lift to the cotangent space. And the lift, these kind of lifts are always Hamiltonian with respect to the canonical symplectic structure over this space. Therefore, we have a canonical moment map, it's rep QVW. No, always. when we lift an action of a reductive group over a variety to the cotangent space of the variety, we always have that this action is Hamiltonian, and the moment map can be chosen in a canonical way to Lie of GB. And okay, now Lie of GB is the direct sum of Lie algebra GLBI. So we can always consider inside Lie GB an element lambda in C Q0, which is just lambda I considered is embedded diagonally. Is that clear? And then we can choose a character of our gauge group. Character. This one is just Z rational character. This one is just Z to Q0. Sorry. So I'm going to talk about theta in Z to 0. Yeah.
Sorry, let's ask a quick question. When you write phi with the borrowed, does that mean all of the vector spaces, or is there some dependence? Like, is
Well,
phi dependent on a particular vector space?
Yes.
Just a fixed notation.
You mean the R here?
No, you say you write phi in W, like just phi in W places.
Yeah.
Does that mean like all of it? That means that's
Yes. For all these arrow, I have a map. So I am taking the direct sum for each of these arrow, and for each of these arrow, I'm considering from, for example, if I take this blue map, this blue arrow, from W0 to B0,
Okay.
up to choosing a basis. Having a dimension vector is the same to have vector space, right? We can consider C, B0, CB1, CW0, CW1.
So phi without a subscript is like either things.
Yes.
Yeah, okay.
Yeah. Yes, exactly. Sorry, yes. You technically I have it. But yes.
Thank you.
And okay, so I fix a stability parameter, which is an element of the algebra. I fix theta in with lattice, which is equivalent to a character of the group or stability parameter. And then we can define our Nakajima variety. The Hamiltonian reduction with parameter lambda and theta of QD of T star ref Q dW, which is defined like mu inverse lambda GIT quotient of stability parameter theta GB. GB and 20 también. Okay. Can I assume that the GIT quotient is a bit clear? Okay.
I think that people know what this quotient is, right? Yeah. Am I right about that? Anybody not know what these quotients are?
Okay.
The thing that's probably less well known, though we've discussed it before, is what these representations are, right? I think we have discussed them by now. So everybody's okay?
Okay. Okay, and let me note just one thing about this isomorphism here, this correspondence. For I denote chi theta, the character corresponding to theta, and chi theta send an element of GV to the product of the determinant of GI minus GI. This is my notation. Not mine, the notation I'm using. It's quite standard. Sometimes they use plus. Okay. So we can start to talk about varieties. The first concept I have to introduce is the notion of both. Both can be thought like a generalization of quivers. Just in the sense I'm going to explain the meanings. But like starting from the Cherkis definition of both. The Cherkis define, okay, with a quiver is a collection of vertices and arrows between these vertices, right? Now it's going to take a bow, a collection of distinct closed intervals from R and in particular oriented. I mean, any interval is oriented. For example, 0, 1, 0 is the starting point, 1 is the end point. And I'm going to denote them by a generic interval will be denoted by sigma, and graphically they are represented by wavy lines. This one is an interval. E are arrows, but this time arrows have to satisfy a property. They have to start from the endpoint of a wavy line and they can only end at the starting point. So for example, I can have something like this, but I cannot have that.
So I'm gonna move the computer over here. Richard has his soul well down. I don't have to move every time, I just need to move the computer. With an experiment. Well, don't don't stop, you can go.
Okay. So we cannot allow to have such an arrow. Okay. But this one is a bow, but now there is the first problem that if we are considering, if I give you this definition, there is the natural notion of length of an interval. That we denote as sigma, the length of sigma. And now Cherky says that, okay, when L sigma goes to 0 for all sigma, then both goes to quiver. The bow go to a quiver. This is quite clear, right? Because instead of considering an interval, I'm considering a single point. So there is no end point, starting point. I just recover. But the point is that when we construct bow varieties in sense of Cherkis, and we prove the equivalence with the algebraic description we have, but this is clear also for Cherkis, clearly. The length doesn't play any role in the construction of bow variety from the algebraic point of view. So we can just think both, right, as quivers with oriented vertices. Is this clear? If you have any questions, please. But the length doesn't count. It's just a vertex with an orientation. And this last point of view is basically the point of view of Nakajima and Takayama in the paper in which they start to translate this construction. Okay. I think. Okay, yes, just let me know that. No, okay, I'm going to not this.
Can you have a review language mode on the system?
Something like this. I want to make you this question later. Technically, from the definition of Cherkis, no. But in the paper of Nakajima and Takayama, they are considered, and the variety we get is the and so and
there's no suction in
Yes, the Bow variety we obtain is the moduli space of solution of NUMS equation on the sheet. It's just, and this has been proved by Takayama in 2015. Yes, but technically this is not hollow in this like I define now. Because the intervals are inside R, right? So it's not clear how to have this starting point, ending point of an interval.
No identification.
It's not clear from the differential point of view, the checklist point of view. From the algebraic one, yes, there is no problem in defining a Bow variety with this diagram. And what is the do you see the eraser?
About the board.
Oh. Okay, now I'm going to define the Bow diagrams. These are called by Cherokee Bow representations. In a different way, maybe at the end of the talk, if time allows, I'm going to explain. And the point of this definition is that you can think this new data as a generalization of B and W, the dimension vector in the frame one. And I'm going to explain this connection, but later. And okay, so given B, okay, I am assuming to have fixed a bow for the entire talk. And I'm taking a pair, lambda and B, where lambda is a collection of X points. Okay, I'm going to use some color now. Okay, I can take some X points over H interval, whatever, also 0. And this is lambda. Now, if I take X point, I am dividing my intervals into segments, right? Usually denoted by Z, Z0, Z1, Z2, Z3. And for each segment, I am considering a dimension vector space. So B will be DZ, where Z is a segment. Okay, inside an element and segment. So let me know this. If lambda is empty, I have just a dimension vector for the quiver with unframed. I don't have any way to put W, right? And okay, later I'm going to show how from here, in particular case, we can recover that case. But now, for physics, I choose this color because I think these are the colors you use to define brane systems, right? Red is MS5.
Is it standard? I'm not sure. Maybe it's standard.
No. Okay, in the paper I read, they use it. I don't know how to define an NS5 brane like this, so I'm going to remove it. And so these one are the 5, yeah. And then each segment is going to give me this one is the dimension vector, and D0 is the number of D3 branes. The same for D1, D2, and D3. So
dimension of is it a V? Are those numbers in VIs or?
yes, when are little are numbers, so it's a dimension vector. When I put them big are vector spaces.
Okay.
But I'm not going to write them big anymore. And okay, this is the relationship between So we have on a side a relationship between bow diagrams and Quiver diagrams, Quiver plus frame dimension vector. And there is also a correspondence between brain systems and bow diagrams. Indeed, in particular cases, has been proved that bow varieties will be column branches. And in the sense of Bruggeman, Finkelberg, Nagashima. And indeed, in this context, the length of interval, if I'm not wrong, should be the distance of brains. I think. Probably, I mean,
Yeah, you have many directions. Yes, perfect.
but I think Professor Rani knows how to define that in terms of distance, right?
Yeah, every weekend, founded by Tuesday. And in the simple that we go to the sixth direction and the sixth.
So you're saying that so there should be more S5 in this picture, or they just have infinity?
Which picture?
Which one? This one, right? So you say each squiggly line has
I
two
can.
NS5s in it, right?
Do you need more NS5?
Oh, I'm just asking if it's there.
I can add and doesn't change our construction.
Number of elements will give you input.
But if you want, I can add here and also here to NS5, and choosing a particular dimension vector, the bow radius doesn't change.
But critically, the floating points are I can accept with the. It's not on the line. I see it. So it's something.
Let me just remember here, maybe what all the directions are, right? So there's 10 directions, right? So there's each the D5 and the NS5 are sharing 2 directions, is that it? And then
One.
sharing 1 direction.
Well, so transverse or challenge. Well, they share 2 plus 1. Then transverse is 1.
Okay, they share 2 directions.
2 plus 1, 2 stays 1.
2 plus 1, okay. They share these 3,
2 out of nothing.
2 out of none. 3 out of the 10, okay.
Then there is an R3 times R3. By the R7.
Okay.
7 plus 2, that's the 9. Then one of them spans 1 R3, the other spans the other R3. And now is what one of the interesting stuff, how, or in this case, it's this one. Okay. So this can be periodic, even though it's not necessary.
But we had a useful chart here, though, right? So the horizontal direction is the interesting direction, right? So there's the horizontal direction, which is the interesting direction. This is the one-dimensional, right?
Yeah.
1 dimension. And then the other 2 directions at the end, that the D3 go are then the same as some directions that other brains go. We have this. What's the right way to do this? And we have
I don't see what you are.
I'm trying to write what the directions are. So this is the D5, some of the D5 directions, right?
That's an R3.
An R3's work. And then we have the going up to the NF, that's also an R3. And then here going this, we just have a single R, right?
Oh, S1. It's big deal, it's S1 because it's identity.
Right.
Yeah, and it doesn't really matter whether it's R or S1, you just need to reflect.
And then
you put the other thing.
And then that gives us 7. And the remaining 2 are shared by all the brains, yeah. Class and R3. So the length is this distance along this direction.
in this direction.
So do you know how to define if we put this red circle you already erased? So how do you define this guy? Like we have some funny topology in this space. No.
I think for if I take something like this, right? And
So at the moment we have this this horizontal direction, the moment is either going to be R or S1, so we're difficult. We have difficulty doing something else with this direction. I guess this is the problem.
yeah, but in this direction, if I take the
Yeah, that way it's okay, but
Why do you draw the red line as a line and not a weekend?
as a line, no?
Not a weekend. Why don't you make a distinction between those two? different-
although the wiggle is the is this R, that's one direction, we're going along, we have a wiggle. The orange, the red arrows are actually indicating the presence of an NS5 gradient. Yes. So normally, the NS5 gradient is supposed to be perpendicular to this red line.
Oh. So in this picture, you have, only one. Okay, so we need to, change the diction.
So somehow, if you have a squiggle with this red thing here, then what that would mean normally is, if that were all you had, is you would have an S1, and you'd have like one squiggly line going on the S1, and you have a single NS5 grain on the cutting. But now if you have this picture up there, then you would need to have a more interesting topology than just an S1. You would have this S1 at the left, and then you have an addition, an interval coming on from it.
So in order to clarify the dictionary, we will have to draw the case where you get the Quiver.
Yeah, I'm going
So
the
I think in some conventions, people will use a circle to replace those red lines.
it puts with the red line.
Yeah, instead of an X, you could have a circle, this is of course true. But the difficulty comes from the fact that we don't end up getting something that's on an R or an S1 here. Right? So if you're on an R or an S1, you're doing a type A, what's called a type A curve, and that will work to do this circle. As long as you wrap around. But if you want to get an arbitrary Quiver, then the circle won't work very well.
So, I have a question. Why are we insisting on working in type 2E? If there's a certain level of space time, then doesn't it make sense to degeneralize and work in 2A? No? But then why is it one? Because it's necessary.
Change the.
So basically, as far as I understand it, it's these general flows we're doing here are difficult to interpret in terms of brain systems because of this difficulty that we don't have an R and S1, we have some more general graph happening. But in the type A case, this is what's done in Nakajima and Takayama, it's fine. And in type D case, there's also an interpretation using oriented folds. I guess we'll get to it sometime.
This was common.
Which comment?
Can you make the most general overwriting which gives us quick? You wrote some 3D.
Oh, the more general one, yeah, it's don't disturb it. Disturb. It's just if over each wavy line, I have the same number on each segment.
Then what's the quick?
Yes, that's the Nakajima Quiver, right?
What?
So you can give.
Oh yeah, the Quiver is just replacing I with vertices and the arrows are there.
Can you?
Okay, for this.
Go next week.
Yeah, yes, but No, I need a bit of time. I mean, it's just this. For example, if I take in this case, for example, this one is the quiver. This two gives the dimension factor here, one is here, the number of edge points is the tree. And with this,
Okay, so you could see that you have two images. There are, that's it. There's no, in the previous picture, you had the line which goes from one end to the other. Here we go.
but
Wasn't this supposed to be a two
Yes.
framing?
Only two.
yeah.
Framing as a two, because you have the number of x's. Yeah.
Each interval is a vertex. And if for each interval there is one dimension used, then one is the dimension of the vert I put on the vertex. And the number of X point on the interval is the dimension of the plane. This one is the correspondence field.
You cannot get such a quiver. But you should be collected.
Well, we cannot get a brain system out of this either, I guess, because of what we were saying, right? If you get rid of that loop, then yes.
The loop is fine, but
But
then
with,
it's not on a circle.
right, that's right, yeah. But if you put in that loop there,
Put in the loop, you don't have any more brain system. And then I think you're stepping away from the checklist is the definition, because he was defining the brain system.
yeah, this is the question.
In the abstract definition, we are allowed to add this. I mean, the one is the definition of both, and the one of diagonal. We can have such a construction. We can construct the associated varieties. I don't know if these are meaning in physics, but
So,
we can do that.
right, so the goal was to give a generalization of this bow variety construction.
Yeah.
That will give you an arbitrary quiver. And it seems in Cherkas's definition that he was allowing this, but I'm not sure how much discussion they have of examples like this one.
Yeah, so as far as I can tell, this dictionary, the boundaries of two wiggly lines. Yeah, the boundaries of two wiggly lines is Bishop's Python, but every wiggly line has the line, solid line next to it. So you could also associate the solid lines and the Bishop.
Solid line, you can associate a solid line to what you say?
The Bishop Python.
Right,
So you have this.
yeah,
Two wiggly lines. So those will be segments, two segments of different length. And there is one and plane in the field, that's the solid line. And showing two. In this extra circle, I don't have it.
yeah, so. I guess this was the question, whether one can make sense of a more general quiver. In terms of, brain systems. You seem to be saying not, if it's not on a line or on a circle, you can't do it. Except for maybe this orientifold situation. Right.
For example, if I just consider the circle, the corresponding navigation of varieties, maybe putting some X point should be described in terms of Hilbert schemes, right?
Right,
So has a perfect meaning in math.
that's right, and even in physics too, but maybe not associated to a brain system. I mean,
It's not in isolation. If it was in isolation, would it be? It's not. Extra frequency.
okay,
And then it's certainly not the same.
Well, this is not a symmetric product, but with the extra stuff, yeah, that's true, yes. But anyway, I mean maybe, but there's other things you can do instead of having this circle, you can also have like a tree. You can have a graph, you know, it has like a line and you have a branch, right? Like the type D is one of those, but type D you say you can interpret, but maybe a general, if you have longer branch, maybe you can interpret it.
These is special case. Because, only 2 months. Each, you have finite D, you have to have a fine D,
Right.
but, E you cannot do.
D type E you cannot do. Yeah, so it's quite restrictive then. Okay, well. We were hoping that maybe maybe we would be able to do something for more general quiver, but that's all right.
Okay.
As long as you have the formulation and using the block type representation. Suppose it's consistent, and done. But
Yeah,
probably not before, but
No, I mean it's nice to have it though, because of the fact that we want to understand what the physical meaning of these construction is, right? So- all right, so but can you maybe you should continue and
Yeah. Okay, I'm going to show how we construct varieties. And then I will show in which sense we recover all the Nakajima theory. And okay, so let me suppose I have fixed ball diagram. And so just okay, just something like this. And for any x, we are going to construct 2 spaces. For any x, the building blocks of our construction. For any x point, we start defining a space like this. We take over the x point, let me suppose that point is. We have this vector space here, this vector space here. For that point, give me a map here, which is represented by A1. A map, the x point is such like a framing, right? So I'm going to define a copy of C and 2 maps going from the left to C and from C to the right vector space, and then other 2 maps here. But this space is too big, and we consider something I'm not going to define properly, but we are going to consider a locally closed subspace of this one. It's an intersection of a closed and an open subspace, which can be considered is isomorphic, like the moduli space of solutions of Nernst equation on an integral. So for each x, we basically on the differential point of view, we consider, for example, we can take from the middle point, and we consider the moduli space of the solution of Nernst equation. This one is m tilde x and corresponds to the such data satisfying some algebraic properties. The second building block I'm going to consider is for any arrow as I have something as like a segment here the tail of S and the and the head of S. And we are just going to consider the cotangent space of the homomorphism from VTS VH. So this one is the analogous part of considering the representation of our underlying. The underlying quiver for me is the natural quiver associated with both, which I obtain by replacing every interval with a vertex, and the arrows are the same. Now, okay, from our data, we have a natural gauge group, which is given by the product over the segments of GL VZ. For any vector space, I am considering the gauge group given by the product of general linear group for each vector space. And now I can construct a big variable just M, which is given by the product over the X point of this moduli spaces of solution navigation on the interval times the direct sum of the quiver part. So for each arrow, I'm going to consider this and S. And okay, an element here is a collection of maps within the vector spaces we are considering. So we have the natural gauge group, the natural action of the gauge group. And we can prove that this action is Hamiltonian with, okay, a consideration. MS is a symplectic manifold variety. M tilde X has a natural structure of symplectic variety. This is a result by Urtobil, 89. I think. At least the fact to describe this moduli space as these matrices has been proved by Unspeed in description.
So he proved that the moduli space is given by some subset of this MX, you're saying,
Yes, exactly.
which you didn't describe yet for us what the subset was, but it's some subset.
I don't know. I'm going. Do you think it's the case of
Okay.
writing the conditions?
Maybe.
Maybe I
But,
showed us in the examples.
Okay.
And so we have a moment map. And
Does anybody then mention that specification maybe this groups into daytime? You know this somebody?
Embedding of discrete group into. I'm not sure if I know that's
This construction means maybe.
What's the connection between embedding discrete group and this
Custom input from partition problem.
Okay.
And that's this way of taking relative things. What about the doublets? And you think of it as a partition problem. And the partition of the sum of doublets into this.
That's
So each such thing corresponds to an embedding of the discrete group. The whole that sum is into the corresponding data function. If you do D, then it will be the D line.
The sum of W's means the sum of the number of X's, or? What do you mean by the sum of
No,
W's?
The actual sum of them. So every W is a number,
Yeah,
and so you just sum it up. This gives you an integer number, which is in, so you declare it to be an integer group.
okay. But I don't know what the W's are, though, originally. For a quiver,
Bunch of vectors.
the framing.
Yeah,
So you take a framed quiver, you take the sum of the framing dimensions, you take a cyclic group of that size, the sum of the framings, you see?
yeah.
And then,
Each such assignment of numbers gives you an embedding of this second group into the corresponding number. This is what determines the unit.
the algebra given by the gauge node, you see.
Well, the linking diagram which you however number of nodes.
So you want to have a Dinkin diagram for your quiver. And then you have the framings, and you take an embedding of the cyclic group of size given by the sum of framing dimensions into this B algebra for the quiver. And these are related to the problem of the solutions of Nom's equation, you think, or?
No, this is given, so this will give you the quiver. So there is a map. And so the map is between the quiver and this embedding problem.
You have a map between the quiver and this embedding problem of embedding cyclic group into type.
Yeah, in
Whatever.
the corresponding
Okay, yes. So for each quiver, we get an embedding problem, yeah. That's what you're saying, yes.
and so I mean you could either make this connection or not. Right?
But what does the embedding problem have to do with what we're?
In the brain system, you will have to face such a problem, especially if you give the question of which brain is asking. Because Bush wanted to make the speed one, and then when you do the figure, I think you have to face it's embedding.
To do T duality, you say you have to.
There is some operation which is called duality.
I see. And that involves solving this embedding problem. And it's a T duality is an operation you perform on the quiver, or an operation you perform on the brain system. Okay. But in order to have a brain system, we need to be in the type A quiver, right?
Then you are in the type A, just like in the past.
If you're in type A quiver, then this embedding problem can only be relevant to brain system in type A, right? Or maybe type B if you're doing work with.
But it could be equally do this very important. Type B.
Okay, type B as well. Type B or type D, okay.
I think we're I think the mixing between string theory and algebra. So when we're talking type A, type B, it's a string theory background.
Oh, I see. Oh, I see, okay. Okay, okay, so yeah, we don't know anything at the moment about this embedding problem. But if it's Katz, Victor Katz, you're saying, Nicholas? Victor Katz, yeah, so then I guess it's something which we should have known.
So there are natural extensions in the technique which are not into algebra. There are some contributions to mystic to calculate the once explained for the process and
I see. What does it mean to embed a cyclic group into a Lie algebra? You mean the Lie group, the group associated to it, or
Yeah, the group are associated.
the Lie group? Okay. Like the simply connected one, for example.
Yeah.
And we're looking at embedding the arbitrary cyclic subgroups of this group, or we want to take a in the center, or
Yeah, that's solved it for any ABD, so.
Oh, okay.
It's a sticky group and any ABD.
This is an example that two within SU, SU,
I see.
SU3 or SU4.
Okay.
And then like the normalizer, because then it's a partition problem, we can divide it into two, like into the partition of the nodes. And then the left untouched part will be the normalizer of this Z2 coordinate. So
I
it's,
see.
so normalizer yes.
Sure, we can explain to everyone, right? So just-
Ah. Yeah, so but yeah, I draw this graph here, but
Just not to wait, well, I just wanted to know if there is anyone made a good point between this.
Yeah, so okay, so maybe we talk about this later, but
yes, yes. because
Right,
it's
something
very-
about
it's
it,
a
so,
very common topic.
Victor cuts. It's completely unrelated at the moment to everything else. Looking at embedding. We classified some kind of embedding of a cyclic group, say, maybe other groups. Or other discrete groups.
Yeah, that it's not by me. So
Okay, so
there were some extensions here. Okay.
to simply connected.
So. As for negative of the variety, we can take the diagonal embedded C segments inside. But in order to take okay, we have a Moen map, we are going to take the Hamiltonian reduction, we need two or one with a chi parameter. In order to take a stability parameter, we are not considering all the possible diagonal embedded matrices, but just the one on first segment. So I first segment. And then let's take chi the character. And now the variety is defined of the formation parameter lambda, the B parameter chi associated with B lambda V is just defined as minus mu minus 1 lambda GIG quotient of the B parameter chi, the gauge group G. Okay. Now I would like to show some examples. Let me consider, okay, for example, zero and zero. We can, okay, looking at every GIG quotient as that can be empty of the substate induced by the stable locus of the variety. For variety, the stable locus is always more. And using such consideration, we can deduce that this variety for any n greater or equal than 0 that exists, and it's unique, which means it doesn't depend on any parameter. of dimension, it's affine, it's smooth, and the dimension is 2n. Just two examples, n equals 0. It's clear that I can have just one point, right? I have only one element there, and n equals 1. Okay, what are our base maps? So okay, we are going to take n0, cn 0. We have such a picture. Then we have to impose this condition on each triangle, and they just require me that, okay, I don't have this map because it is 0, I don't have this, I don't have this, and I don't have this. I have just these four maps here. And we call this A, B, B minus, B plus, B minus. Because this one is induced by this x point, and this one by this x point. The first thing we have is that A and B must be different from 0. And this one is our m there. If I take mu minus 1 lambda for any lambda, the only condition I have to add is that B plus is equal to B minus. Because let me remind that this lambda affects only the maps on the first segment of each interval because of how we chose that. We are just embedding CI into the algebra or gauge group as diagonal matrices placed on the first vector space on the first segment of each wavy line. But here is 0. So no, sorry. Okay, let me just write 0. Is it clear now?
Sorry, what is mu versus 0?
Just
It's a condition that B plus equals B minus.
yes, just this condition.
We're supposed to believe that because you have you didn't give us a formula for mu in general. You just want us to believe that in this case. That's the only thing that you can do.
Yeah, just for time, I think.
There's some term of mu, which is the difference of B plus and B minus. And that's the only term that's non-zero in this case, I would just say.
But now this space is just C times C cross times C cross.
This dimension equals 24, that was from something earlier.
Sorry? Yeah, no, this
2n,
one.
okay.
Yeah, the
2n.
dimension is 2n.
That was a cool. 2n.
So for n equals 0, I got a point, and it's 0 dimensional. Here, I should recover two-dimensional space. And okay, but now the gauge group acts on this space, changing the base of this C, right?
Would you be writing a Quiver for this?
This is just a single node of UN.
That's my question.
No, there is no Quiver version for this. And it's not the way we associate a both are Quiver, because it's not cobalanced. Doesn't satisfy the condition that on the same wavy line all the dimensions are the same. I don't know. We hope to find something like that. Yeah, we don't have that.
So how would you compare it to the modular space of one node, what the sure one node with label.
Sorry, one node, you mean just one wavy line?
A quiver of node of UN gauge group.
And
And yeah, just it. the Quiver.
What would you compute the nominal space, and is it equal to what you're?
Now, if I have just these,
Yeah, the Coulomb
I,
branch.
But you don't have a notion of two.
no,
Mhm.
but I need to add framing, right?
No, just a single node open.
So we would say that what you just do would be Coulomb branch or this.
The Coulomb branch is the,
Coulomb branch is this Quiver. Quiver was, it's a space which was considered by Tiziano. And they discussed.
So probably this one should be the variety associated
This is not too
to these, I think.
It does, yes. So it's ideal. Oh, I see, yeah.
I think probably from the, if this one is, you are considering column branch here, I should take
It's different than what you do. So there
this one, right?
You have an extra loop. This one would have an
Yeah.
extra loop.
This one will be on with loop attaching.
I don't know.
So if you continue, let's see what we'll get. First.
Okay. We have G, which is just given by GL1 in our case, so C cross. And an element here acts here by sending B in B and sorry, C is 1.
oh, yes, see, this is supposed to be a Coulomb branch because this is a balance. So you have the co-balance and the balance set.
Yeah, that's right. You get balance. I was thinking about
balance, so that makes it a Coulomb.
No, yes, this is, yes, has been proved.
You're applying this notion of zeros, right? The balance and full balance are good in each other.
Yeah. This is balance, in fact.
Yes, this one is equivalent to this construction, and this is a balance applying type A, and so it's the column branch.
Yeah, so, so for this, you put zeros everywhere, right?
No, just on this, and this.
And then you put the inverted and put n not between two x's, but on a single wiggle line
Here,
like that.
and here,
And here,
So you could do the mirror symmetry. You replace the x's by the ns by.
yeah, in
So you replace x's by arrows.
this one is the Higgs branch now,
yeah, now it's the Higgs branch.
Yeah.
and indeed it's co-balanced, and we recover Nakajima's chloride.
And this one,
This one,
There's 0 arrow to m arrow to 0. Then so it's just the same as an m with no arrows above.
so
Coulomb
then-
branch of just an m, just a GLM acting on the 0 presentation.
yes.
Which is this thing that we were talking about, this universal centralizer.
Yeah. But Tiziano, you did not call it the universal centralizer.
No,
You agree that this is the universal?
I don't know that.
I guess that is what it is.
What is the universal central?
So the universal centralizer, we're talking about you look at the family of centralizers of all regular elements of your Lie algebra. But of course, centralizer of an element is so you can have many different elements which have the same centralizer. So you want to put them together to get the base of just the centralizers for each different centralizer. And so the base of this centralizer scheme is just the image of adjoint quotient. It's H mod W or G mod adjoint quotient G. And over each of those, you have the centralizer of the regular element of that. Orbit closure. Adjoint orbit closure. That makes sense?
And then we would call it the modular space of n.
Anyways, if I perform the GIT, the action of G, which is just C cross acting its way, is free. So it's just the usual quotient, and we recover C times C cross, which is two-dimensional in modern line.
Here is exactly the Coulomb branch of U1, single node view.
To be that. And okay, do I have how much time?
Well, yeah, we should stop soon, but
Well, maybe I can state the relation with Nakajima.
yes,
Right?
let's do that too.
Okay. I have also calculated the example in which your supersymmetry breaks, and it's a such like we have a general phenomena in which we have empty varieties if they respect that condition. Then I can show you later maybe. Okay, now the condition we have to, in order to have a Nakajima Quiver variety, we should consider co-balanced both diagrams, which is just that B lambda B such that for any x, this one x, this one is bx minus bx plus, I define that they are equal. If for any x, my Bow diagram with respect to this condition is called covariance. And now B is, assuming that this one is covariance, I have a bijection between this and Q, B, W. Because, okay, B and Q is the correspondence I was talking before. Intervals are points, vertices, and arrows are arrows. Now, if B is cobalanced, for each interval, I have just one value of B. So B here should be in n segments. But since cobalance is the same like considering it in Ni, instead of interval. W is defined like W sigma equal the number of x points on sigma, where sigma run over the interval. So for example, let me consider this covalence case. One. The quiver is just one node. D is 1 and the framing is 2. And now, okay, let me remind that lambda is taking in CI for both of the theories, right? My deformation parameter is an element of CI, not just C segments and C Q0. So it can be considered both as stability parameters for the Bow theory and the Nakajima theory. Now, when I consider the character of this G, technically I have much more characters with respect to the linear, the gauge group of the Quiver theory, but we have proved that okay, this one is a character, is an element of Z2 segments. But so I can take even here. But I can take an element in Zi embedded in Z segments via first segment. Just by going from here to, I don't know, sigma theta is equal to, okay. Trust me, we can just choose a parameter here and the theories are equivalent. We recover all the Bow varieties by choosing stability parameter here. So I can take theta in Zi and consider this like stability parameter for the Quiver theory and the bow theory. Okay, where, let me just notice a fact, G can be written like the product over sigma, which is first segment, GLBZ, Z first segment, GLBZ, and all the other one. Right? This one is my gauge group for the bow variety. But this one, in the case of cobalance case, this one is nothing but the gauge group of associated to this Quiver theory.
The second factor is all the other after the first segment. The second factor is all of the ones that are after the first segment, is that it? Or what is the second factor?
Yes, yes, it's the remaining
Remaining segment.
sigma, not the first segment. And this one is GB. This one, let me call it H. Okay, when we perform these portions, these Hamiltonian reductions, we can divide it into two steps. So we can take M and take the Hamiltonian reduction with parameter 0, 0 by H. The remaining action is given by the gauge group of the Quiver theories, right? And indeed, we recovered that this one with the GB action and the induced moment map is just isomorphic as symplectic Hamiltonian G variety to T star rep QB W GB and the moment map for the Nakajima theory. And now it's clear that if I perform the GB Hamiltonian reduction, in this case, I recover the bow variety, but performing Hamiltonian reduction here is the same as performing Hamiltonian reduction here. So bow varieties are isomorphic to Nakajima square varieties as Poisson algebraic variety.
What is this notation?
What notation, sorry?
You say T star,
Yes, the cotangent space of the representation space of QBW.
what do you call
Q is the quiver, B is the dimension vector for the quiver, W is the framing dimension vector.
yes, and what's the definition of the notation?
Oh, it's just okay. And maybe it is rep is equivalent, or this space is the equivalent to
Reduction problem?
yes. And it just is okay. Let me define this. This one is the direct sum without the cotangent part before obtaining the cotangent space. I, J, an arrow in Q, homomorphism from CVI to CVJ, direct sum, the direct sum over vertices of homomorphisms that go from CVI to CWI. So an element here is a collection of maps, one for each arrow. For each arrow of the framing, I have a map. The collection of this map is a point of this space, and then I take the cotangent space of this space.
Without any additional action. It's just
I mean, the action is given by changing basis of CVI by the gauge group. I'm changing the basis. And then if I have an action of a group on a variety manifold vector space, I can take the leap to the cotangent space. And this is the action we're considering here. And so these are Hamiltonian with a canonical moment map. And these are the data I have here. and performing Hamilton reduction here, I recover Nakajima square variety. And what we have proved is that this object can be identified with this Hamiltonian reduction, which is obtained by decomposing the Hamiltonian reduction to obtain both varieties into sets by dividing the gauge group into the gauge group of Nakajima square varieties more the remaining parts. Okay. And for example, in this case, M00 is equal to the Nakajima variety associated here of 00, which is the new cone of S2, which is just the double cone. I probably don't have time, otherwise I show calculations. The idea, it's quite simple, because if we look at the space we have, in the covariance case, this one is just the direct sum of all these spaces is equivalent to the cotangent space of the representation of Q with dimension B, without the failing part. But our conditions here in the cobalance case say us that A must be an isomorphism. So what we do is pushing every map as a map on the fourth segment. Is this idea clear? And after this operation, that doesn't make sense that quotienting out by H just remove the more data, which are unuseful now, are isomorphism of spaces up to changing basis. And the only thing that back in some sense is the gauge group of the Nakajima theory. I think maybe it's
Shall
fine.
we have lunch then? So, let's thank Tiziano. So everybody is free to get lunch. You can bring it back here. We have the room until 1. I have to teach at that point, but then I will find everybody after that. So maybe we'll have lunch, and then after 1, you can move to the 6th floor room, the physics common room.
Okay, so
For those of you who want to discuss.
after lunch,
Yeah, but for those who want to continue discussion, after 1, it'll be the physics common room, 6th floor. Okay,
physics trouble, yes.
and then I will find you at 2. Hopefully, that was overall on the camera, but can you
Do you